Hello everyone, welcome you all at Lokesh Sir Unlimited Study Zone. So guys, in the chapter Wave Optics, today we are going to start our last and final topic of the wave optics, that is called diffraction of light. Okay, so first we have to understand what is diffraction of light. So the phenomenon of bending of light around the corners and the encroachment of light within the geometrical shadow of the opaque substance is called diffraction. Means when you have a sharp edged corners, okay, like this, this is the very sharp edge corners. The upper one tip of this edge is very sharp. Okay, this corner is very sharp, and you have a particular wavelength of light. Now you know a ray is not permitted to encroach in the this area where the obstacle is presented. Okay, but you see in the phenomenon of this wave optics, the phenomenon of bending of light around the corners and the encroachment of light within the geometrical shadow area. So this is the shadow area where the light is not permitted. Where is shadow? You form the shadow where the light cannot enter. So it will cast a shadow of the opaque obstacle. But there the light will encroach. This event is called diffraction of light. Let us understand. Here this is a slit and this is the source now, and this one is the screen. Okay, if you blow a radiation of light here, then what will happen? Yes, see, the light can present here. So this is the white one area. Okay, light is admissible here, but these are the areas where light cannot enter. Means these are the area of the shadow. Clear or not clear? So black areas are the shade of the arrow, and this bright area is lightning area. Clear? But what happening actually? Yes, this like event takes place. Though light is not permitted, okay, to enter in this area, the black one area, even though some light is there, okay, and this is called some type of encroachment of light in the shadow area. Okay, so the light ray covers some of the area. This is called diffraction by a slit. Okay, diffraction at a slit. Clear? So now you can feel the definition that phenomenon of bending of light around the corners means what happened? Light get bends here. Okay, this is the bending of light. So light bends here as a form of wave, sorry, around the corners, and there is the encroachment of light within the geometrical shadow of the opaque obstacle is called diffraction. Now see another way. This is again your source, and this is obstacle. Previously it was a slit, because slit is the opening for a source, and slit, this is obstacle. Clear? Now if this is obstacle, you blow a light beam here, then your pattern should be like this. So here the light area, the visible area, and this is the black one area. Clear? Means shadow area. So you have a shadow of this. Suppose you point object, this is A and B. So you have a shadow looking like A dash and B dash. Clear or not? Okay. But what happened? The light will enter in the shadow region. Okay. And there is some encroachment of light here in the shadow area. This is called diffraction by an obstacle or diffraction at an obstacle. Okay. So this is the definition of diffraction, and x and y are the region of diffraction where the diffraction exactly takes place. You see here the light encroachment of light in these places in the shadow area. Okay, so this event is called what? Diffraction of light. Clear? Diffraction of light can be explained by using only wave theory of light. It cannot be explained by particle theory and Huygens principle. Sorry, particle theory and Newton's theory. Clear? So this can be only explained by the wave theory. Okay. So going to the PDF is okay. So coming to the diffraction. What is diffraction of light? Diffraction of light Diffraction of light is the phenomenon of bending of light around the corners of an obstacle. When you have a obstacle that having size very small, means the size of obstacle, in previous class I said that size of obstacle should be less than size of light, or you can say wavelength of light. Clear? For the persistence of wave optics, this is condition, and this condition becomes very important for diffraction. So diffraction of light is the phenomenon of bending of light around the corners of an obstacle or aperture in the path of light. On account of this bending, the light penetrates into the geometrical shadow of the obstacle. This diffraction becomes much more effective when the dimension of the aperture or the obstacle, yes, are comparable to the wavelength of light. Means when your aperture, or you can say size of obstacle, is very small with comparison to wavelength of light, then this become more effective. Okay, and that time you can see the diffraction in even daily life. Out of the given three cases, diffraction is most pronounced when slit width A is smaller than the wavelength lambda. That is, A is less than lambda. So here are the three cases you can see. So these are the plane wave front, okay, and light is here from the slit, okay. Now check the diffracted wave. Here the size is somehow larger. This is the distance between the slit. It is called slit width, okay. So here the slit width means source width is A, and between the wavelength between two crust and trough to trough distance is equals to lambda. So here A is greater than lambda, means size of slit is greater than lambda. So you will have pattern of diffracted wave like this. Okay. So less diffraction is there. If you talking about the geometrical shadow area, then see only this much penetration takes place. This much only in the impermissible, not permissible region. Yes or no? Okay. Only this much diffraction has been takes place. That is very less amount of diffraction. But now when you decrease the slit, okay, just one. Now see the second case. When here the slit width is lesser than, sorry, it is equal to lambda. Now the width of slit, suppose it is in nanometer, and the you can say the wavelength of wave is also in nanometer. So when these are equal, then the diffraction will takes place in large amount. Now check here the amount of diffraction of wave. So this is slit width. So this should be the non-permissible area. Okay, here it should be outside the non-permissible area, but a huge diffraction takes place here because the amount of light you can see here entered in so large extent. Okay, means diffraction takes place. Clear or not? In the third case, when A is less than lambda, means slit width is very less than lambda, then you will have a great extent of diffraction. Now check how much amount of diffraction. This is only the permittable area, but other than this is non-permittable area, and you can see a large area is occupied by the diffracted wave. Okay, so these waves which are not permitted to come, but actually they have come, so these are called diffracted wave. Clear or not clear? Okay, so this is called diffraction. This event is called diffraction. Now diffraction of light at a single slit. In our syllabus we have to derive the diffraction by a single slit. So diffraction of light at a single slit. In experimental setup, as is a monochromatic light source held at a focus of collimating lens L1 parallel to the beam of light emerging from the lens with a plane wave front WW dash is made to fall on a single slit AB of width A. Yes, so first we have to draw this diagram. So check here in this experimental setup, S is a source of light. So check the diagram. Here S is the source of light. Now if the source of light is spherical wavefront, this source of light having a spherical wavefront, so these are the wavefront and these are the rays. After this lens, this is called collimating lens, the light beam become parallel. Okay, so you have made a parallel plane wavefront. As the light beams are parallel, the wavefront will be perpendicular to this, so this will rise a plane wavefront. This is called WW dash. Clear or not clear? So this is plane wavefront. Now this is your slit AB. AB is your slit, okay? And the distance between the slit here, the gap of slit can be taken as a small d, okay? So this lens L1 is called collimating lens, okay? Collimating lens L1. So parallel beam of light emerging from the lens with a plane wavefront WW dash is made to fall on a single slit AB of width A. Okay, so here in the place of D, you have to take the width equals to a small a. Clear? The diffraction pattern is focused on the screen XY with the help of convex lens L2. Actually, we want to see the diffraction pattern, okay? And these diffraction patterns are made by the different waves, different waves. So to to see this diffraction pattern clearly, I have placed the second lens. Okay, this will focus different rays on different diffracted rays at different position, and you will have a sharp image of diffraction, right? The diffraction pattern is focused on the screen XY with the help of a convex lens L2. Okay, so this lens is used to focus your diffracting waves. Clear? And after the diffraction, you will have different pattern at different places on the screen. Okay, so this lens is only used to focus your patterns. Clear? The diffraction pattern obtained on the screen consists of a central bright band having alternate dark and weak band of decreasing intensity on the both side. You have seen in that Young's double slit experiment, that like in Young's double slit experiment we seen that there is at central always there is a bright fringe, okay, of intensity beta. After then there are dark fringe both the side. Clear? Here it is dark, here it is dark. Again it is bright, again it is bright. And every time the intensity of bright and dark fringe will be same. Clear? So this was we have talked about in interference. But now there is difference in the process of diffraction. At the center, what? At the center you will have a maximum intensity. At the center you will have a maximum intensity. Means constructive interference will takes place definitely at the center. Okay? But now the fringes next fringes are of different intensity and different width. Clear? Now the intensity here, its maximum intensity becomes I0. Here it will be less. Again it will be less, and so on. So you will have the different intensity diffraction pattern will be seen. So this line is important. The diffraction pattern obtained on the screen consists of a central bright band having and weak alternate dark and weak bright bands. In interference, there is no weakness in the bright bands, but here there will be a weakness of bright bands of decreasing intensity on the both side, means upside and downside. Okay, here your diffraction pattern will be maximum at the center. Then next is dark. Then next bright is slightly lesser. Then coming bright are also lesser like that. Okay, let us see how this happens. Okay. According to the Huygens principle, each point on the plane wavefront AB sends out secondary wavelength in the all directions. Okay. According to the Huygens principle, each point on the plane wavefront AB sends out secondary wavelets in all directions. The secondary waves from the points equidistant from the center C of the slit lying on the portion CA and CB of the wavefront travel the same distance in reaching the point O. Hence, the path difference between them is zero. These secondary waves superimpose each other, resulting in the maximum intensity at point O. Yes, what does this lines meant? Okay, see here. Now you can say from here, if a light beam, you can consider this one as source. Okay, now from these two positions, if the secondary wavelet, those are focused at O, will have to travel the same distance. Yes, see, yes or no? From these 2 points, the wave those are traveling have to travel the same distance. So, what is path difference? Path difference from these 2 points A to O and B to O, path difference delta is equals to AO minus BO equals to 0. Clear or not? Path difference by two waves from the point A and B equals to how much? 0. And whenever there is path difference 0, delta equal to 0, this is the condition for constructive interference. Yes or no? Yes or no? So there is the position of constructive interference, and you will have a maximum intensity at the center. Clear? Hmm. So same thing written here. Position of explanation. The secondary waves from the point equidistant from the center C of the slit means this is the center C of the slit. Okay, this is the center C of the slit, and this is the your plane wave front. Okay, from this plane wave front, everywhere rays are traveling. Okay, these are the rays. Everywhere there is a rays means secondary wavelets will be there. Now these rays are equidistant from the point means from this point, like if you're talking about this point, some below than A, just below to A, there is some point that is above B. So this point consider A dash and this equals to B dash. Again, the wavelets have to travel the same distance to reach at point O. Means again, there is path difference equals to 0. So all these points together, the wavelet emitted from here will form a central bright. Yes or no? Because they interfere constructively. Clear? So the secondary wave from the point equidistant from the center C. So C at the center, and some points are above C and some point are below C. Now center C slit lying on the portion CA. So some points on the portion CA and some points are the portion CB. Clear? CB and CB of the wavefront travel to the same distance reaching at point O. So here the wavelets that are traveling towards the point point P, they have to travel, sorry, point O, they have to travel the same distance in reaching at point O, and hence the path difference between them is 0. So the secondary waves superimpose each other, resulting in the maximum intensity at point O. That's why you're getting a maximum intensity at the center. Clear or not clear? Yes, check here in this diagram. Okay, diffraction of a light at a single slit. So at an angle of diffraction 0 degree. Yes, check here. Like mm, first, I'm taking all these waves are parallel. All these rays are parallel. Now this is plane wavefront. So it may be considered that this wavefront, this wavefront is splitted in 12 part. Okay, I consider that this plane wavefront is distributed in 12 part. Now what is happening? Give them number 0 to 12. Now this is your lens, focusing lens. Now if the rays are incident, then what will happen? Same, what same? Same path difference. The two waves from the above one, the 0 one with the 12th one. okay, will suffer the same path difference, or you can say zero path difference, and you will have a bright image at the center. Yes or no? So the wavelets from the single wavefront, okay. So in a single wavefront, there are too many wavelets. The wavelets from the single wavefront reach the center O on the screen in same phase and hence interfere constructively to give central or primary maximum. So this is called central maximum or primary maximum, and you will have a bright fringe. Clear or not? Now now you have to check the condition for diffraction for any angle theta. If there is diffraction is taken place, then what will happen? Slit is imagined to be divided into two equal half. This is a screen. Now this is plane wavefront. Okay, so the different wavelets are there. We have considered this one as 12 wavelets. Okay, and now the wave is diffracted by an angle theta. Okay, the wave is diffracted by an angle theta. So check this angle equals to theta. This is amount of diffraction. So where is your angle of diffraction? This will be your angle of diffraction. Clear, beta? So every time your wavelets are diffracting by an angle theta, now what will happen? Now if your waves are diffracted by an angle theta, so again you will have central bite is there because originally the waves are interfering here. But if I talking about the diffraction pattern at point P1, so some rays, some secondary wavelets will focus here at the position P1. Okay. How? Yes. Consider this is the total path difference from point number A to point number B equals to lambda. Okay. Point number A to point number B, path difference equals to lambda. The total path difference here it is given lambda. Okay. Means the sixth one wavelet will suffer a path difference of lambda by 2. Yes or no? The sixth one wave will suffer a path difference of lambda by 2. Clear or not clear? Okay. It means from here to here, it is the path difference of lambda by 2. And again from 6 to 12, a path difference of lambda by 2. Clear ki not clear? Yes. So the wavelet from the single wavefront diffract at any angle theta 1 such that Bn equals to lambda. Bn is what? The path difference. Okay. Bn equals to lambda and reach at point P1 the pairs 0, 6. Yes, check here. 0 and 6 having the path difference is lambda by 2. Then 1 with 7. Yes, so 1 and 7 again having path difference lambda by 2. 1 with 7. So 1 and 7 having a path difference lambda by 2. 2 and 8 having a path difference lambda by 2. These two wavelet 3 and 9 having path difference lambda by 2. 4 with 10 path difference lambda by 2. Fifth with 11th having a path difference lambda by 2. And sixth with 12th you have a path difference lambda by 2. Clear or not? 6 to 12 having a path difference. So for a path difference of lambda by 2, yesterday we have read that for a destructive interference, delta is equals to odd multiple of lambda by 2, 2n minus 1 times of lambda by 2. So you are getting the lambda by 2 multiplied by 1. This is the path difference. So you will have a what? Secondary minimum. So destructive interference, they interfere destructively, and you will have a path difference of lambda by 2. Okay. And this will give your first secondary minimum. It is called dark fringe. Clear? So at the center, you will have a bright, then it is dark, and so on. Again, it is bright and dark, like that. So talking about the position of secondary minima. Just now we have seen in this diagram, position of secondary minima. Consider a point P on the screen. Intensity at P will be depend on the path difference between the secondary waves emitted from the corresponding point on the wavefront. Now draw AN perpendicular to the perpendicular to BK, path difference between the secondary waves reaching point P, A and B, Bn equals to AB sine theta. Yes, check here. I am showing you the path difference AB sine theta. Now, this was your previous situation. First case, in first case, when you have got your central maximum, that time diffraction angle equal to 0. Okay. First time your diffraction angle equal to 0 means normal situation, diffraction angle equals to 0. Okay. The black lines, in during the black lines, okay, so they meet at a center and you will have a central maximum. Now, if you have diffracting your waves by an angle theta, so this angle equals to how much beta? Theta. Clear or not? Okay. So if this angle equals to theta, then this angle also equals to theta. This is the angle of diffraction. This angle also equals to theta. Clear? Why? Because now this wave front, previously the wave front is like this. Clear or not clear? Previously your wave front is like this. Then that time your rays are like this. Your wave front this one and your rays are like this one. Clear or not? Because angle between the rays and wave front equals to 90 degree. Okay. Now, when your rays are uh, tilted, slightly tilted up with an angle theta, then your wavefront will be also moved by an angle theta. Yes or no? So this angle is equals to theta. Okay, and this is your new wavefront, the dotted one. Clear or not clear? Okay. So this is your slit width A. This is your slit width A. Clear or not clear? Now check the path traveled by the two waves. Check the path traveled by the two waves. See here, the first wave from A, the first wave from A has to travel a distance of A to P. If for a point P, if they forming a image at point P, the first wave have to travel a distance here from A to P. Yes or no? From A to P. Clear? And the second wave from B to P has to travel a path like this. Yes or no? So what is path difference? For path difference, just draw a perpendicular here. So this is your perpendicular. Clear or not clear? So this is your perpendicular. This gap Bn is your path difference. Bn. Okay. This becomes your path difference delta. Clear or not? Now, if this angle is A and this angle is, sorry, not this angle, this distance is A and this angle is theta, then this equals to A sine theta. How? Use the trigonometry. You have seen this equals to A. Clear? And we just draw a perpendicular here. So this is equals to 90 degree. This is your path difference. Clear? And your angle, this is equals to theta. Now, sine theta is equals to perpendicular upon hypotenuse. So by the formula, sine theta is equals to perpendicular upon hypotenuse. Sine theta is equals to perpendicular. Perpendicular here it is equals to delta. And upon hypotenuse, hypotenuse is opposite to the side of right angle. This is equals to A. So delta becomes A sine theta. Clear or not? So what is delta? Delta is equal to path difference. Clear? Hmm. So this we have got the path difference delta and this is equals to A sine theta. Clear? Okay. So now draw AN perpendicular to BK. We have drawn a perpendicular BK. Path difference between the secondary wave reaching point P from A and B. So there are two positions. Upper position is A and the lower position is B. So the difference of path between the two waves, those are reaching at point P, like some waves are traveling here. This is point P or okay. So waves are traveling from A and reaching at point P, and waves are traveling at point from point B and reaching at point P. So you can see there is some path difference. The BP having the bigger path and AP having the smaller path. And you find that this path by just drawing a perpendicular here. This was the slit width A. And you find that this path difference, this much is equals to A sine theta. Clear or not? So this Bn equals to AB sine theta. In the place of AB, there is A because the value of AB equals to A. Where is AB? This is A, this is B, and this is the equals to slit width that is equals to small a. Clear or not? Okay, so this is the diffraction process. Now, A sine theta. If the difference is lambda, the point P of minimum intensity. Now see, if this path difference equals to lambda, wait. Now if path difference equals to lambda, P is the point of minimum intensity. Why, sir? But yesterday we have seen that whenever there is a path of lambda, n lambda, for n lambda, the path difference n lambda, there is constructive interference. Yes or no? We have seen yesterday interference for a path difference of n lambda, the position is of constructive interference. It means lambda, 2 lambda, 3 lambda. There is constructive interference, and for phase difference of 2n pi, there is constructive interference. But today, for the path difference of lambda, if delta path difference equals to lambda, you will have a destructive interference. Why? Because you see, out of 12 wavelets are here, uh, or out of all wavelets are here, if this total path difference is equal to lambda, this means the wavelets still here, okay, will travel a will suffer a path difference of lambda by 2. Clear or not? So the wave number 1 from here, okay, if it is wave number 1 from here to the this one wave also having a path difference of lambda by 2, just like sixth number with the 12th number having a path difference of lambda by 2. We just have seen this in that slide. Okay, understood? And for the case of lambda by 2, they will interfere destructively. Clear or not? So here for the path difference of lambda, previously you got for the path difference of lambda, there was constructive interference during Young's double slit experiment. But here for path difference of lambda, or for 2 lambda or for 3 lambda, you have a destructive interference. Clear or not clear? Okay. So this is because the wavefront can be distributed in divided into two equal halves, CA and CB. What I said, this is the A part and C, and this is equals to B part. So total from wavelet 1 to final wavelet at B, the path difference equals to lambda. So the wavelet till C will have a path difference of lambda by 2 and another part having a path difference of lambda by 2. CA and CB, this is center point C. And if the path difference between the secondary waves from A and B is lambda, then the path difference and then the path difference between the secondary wave from A and C reaching at P will be equals to lambda by 2. Means if you're talking about the first wave from here and first wave from C point, they will have a path difference of lambda by 2. Next, another wave here, this one, and the next one just below this point C, again having a path difference of lambda by 2. Then the path difference between secondary wave from A and C reaching at point P will be equals to lambda by. Also for every point in the upper half AC, upper half AC is a corresponding point in the lower half CB. Yes, just I shown you, like if point for the point below to A, there is a point just below to C that having path difference of lambda by 2. So they will they will interfere destructively. CV with the corresponding part in the lower half CV for which the path difference between the secondary waves reaching at point P is equals to lambda by 2. Thus, destructive interference takes place at point P. Therefore, point P is the point of first secondary minima. Clear or not clear? In this way, there will be a minimum intensity and you will got your first secondary minima. Clear? Similarly, first you have seen your path difference. For path difference in Young's double slit experiment, if delta equals to n lambda, you will have a bright fringes there. But here during the diffraction, when your path difference equals to n lambda, it means for lambda, for 2 lambda, for 3 lambda, for 4 lambda, likewise for n lambda, you will have a dark, interference pattern. Clear? So you will have a dark fringe. Now, so you can make a generalized result for dark, or you can say for secondary minima. Dark is called secondary minima. Secondary minima. For secondaries minima, your path difference delta that we have got as a sine theta, this should be equals to n lambda. Yes or no? For the cases of n lambda, there is a destructive interference. So a sine theta is equals to n lambda. Okay. Similarly, path difference Bn equals to 2L lambda. First, we have taken the case lambda, and then again, it may be equals to 2 lambda, it may be equals to 3 lambda. Then the point P will be in the position of secondary minima, and so on. So, hence, for the nth secondary minimum condition, your path difference equals to A sine theta. A sine theta becomes n lambda. So, this is the derivation for the nth secondary minima. Nth secondary minimum. Clear? Okay. So in these places, you will have obtained your dark fringes. Okay. Now, remember at the center, you will have your at the center, you will have your maxima. This is called central maxima. After then, these are the positions of minima. So this is minima and this is minima. Center, you will have a maxima, maximum intensity. Then here it is minima. Also here it is equals to minima. Clear or not? Now second position of secondary maxima. Here where you will got your maxima. Again maxima. So check if any other point P on the screen such that path difference A sine theta is equals to 3 lambda by 2, then point P will be in the position of first secondary maximum. Okay. So if A sine theta is equals to 3 lambda by 2, then point P will be in the position of first secondary maximum. So check what does it mean 3 lambda by 2. So if your path difference equals to 3 lambda by 2, see in what way your path difference, like the wavelet from here to here and having a path difference, this is first wave and this is the last wave from the pattern AB, wavefront AB, and the total path difference here equals to lambda by 2, 3 lambda by 2, 3 lambda by 2. The path difference you have introduced here, that is 3 lambda by 2. Clear? Means, okay. Position of secondary maxima. For secondary maxima, we need constructive interference. Only in the case of constructive interference, we will have the uh, bright fringes, maximum intensity fringes. If any other point P on the screen is such that path difference for any other point P in the screen is such that for the two waves interfere, they having a path difference A sine theta. A sine theta is the our what this is the path difference. This is equals to A sine theta. If in any case A sine theta becomes A sine theta becomes 3 lambda by 2, then what will happen? You just check. Now 3 lambda by 2 means this whole pattern of wavelets can be broken into the three parts. First half having a lambda by 2, another also having a path of lambda by 2, and another also having a path of lambda by 2. So lambda by 2, then lambda by 2, then lambda by 2 equals to 3 lambda by 2. Clear or not? Okay, so total wavelets having a path difference of lambda by 2. Now check the point from here and here. From here to here, the total path difference equals to lambda. Yes or no? because lambda by 2 plus lambda by 2 equal to lambda. So the wavelet from here to here will suffer a path difference of lambda. So they will interfere constructively and they will form a bright fringe. Yes or no? Again, just below the point A and just here, this one point, you by the diagram you can understand. Again, they will have a path difference of lambda. Yes or no? So again, they will interfere at the same point and will form a bright image. Clear or not clear? Yes. Giving some more elaboration. If there is a point from here to here. Now check what is the path difference from here to here. Again, it is lambda, lambda by 2 and lambda by 2. Clear? So they will form a constructive interference pattern. Clear? Means for a sine theta equals to 3 lambda by 2 means odd times of lambda by 2, or you can say a sine theta becomes 2n minus 1, 2n plus 1 lambda by 2. A sine theta equals to 2n plus 1 lambda by 2. Odd lambda by 2, you will have secondary maxima. Clear or not clear? You will have your secondary maxima. A sine theta is equals to 2n plus 1 lambda by 2. You will have your secondary maxima. So like 3 lambda by 2, 5 lambda by 2 and so on. So we just seen. So for the nth secondary maximum, the required situation A sine theta is equals to 2n plus 1 lambda by 2. Clear or not clear? Hmm. Okay, so reading this theory, if the point P on the screen is such that the path difference becomes 3 lambda by 2, then the point P will be in the position of first secondary maximum. Here we can assume that the wavefront can be divided into the three equal parts. Yes, just I said lambda by 2, and lambda by 2. Okay, we have divided this total wavefront in three equal part so that the difference between the secondary waves from corresponding point in the first two part will be at lambda by 2. They will give rise to the destructive interference. Yes, here it is saying that if you're talking the waves from here to here, so they will interfere destructively. So they will rise a dark fringe. But if you considering the waves from this upper half and the bottom, this one, so they will be have a path difference of lambda. Yes or no? Lambda by 2 plus lambda by 2 equals to lambda. Okay, the secondary waves from the third part remain. Okay, here we can assume that the wave front can be divided in three equal parts so that the difference between the secondary waves from the corresponding point in the first two part will be lambda by 2. They will give rise to the destructive interference. The secondary wave from the third part remain unused and therefore they superimpose with each other, produce first secondary maxima. Yes. Now the wave from here and here. Okay, clear. This one. So check the wave, the path difference. Again, here it is equals to lambda. So they will give a say, maximum, secondary maximum. Now, similarly, if Bn is equals to 5 lambda by 2, then we get secondary maximum of lower intensity and so on. Hence, the nth secondary maximum condition for the nth secondary maximum equals to 2n plus 1 lambda by 2. Means, student, it is just reversed. During the Young's double six experiment, you have got your bright fringes at the position of n lambda, but now you are getting your secondary minimas are there. Okay, and that time Young's double six experiment, you getting your dark fringes there, but now you are getting here secondary maxima. Clear? So this is complete diffraction. Now talking about the intensity distribution, so there is intensity at the center is maximum. Okay, and center at the center intensity is maximum. Then again for yes, this is 3 lambda by 2 and here it is equals to minus 3 lambda by 2. Again you will have your secondary first secondary maxima, then 5 lambda by 2 you will have your third secondary maxima. Clear or not clear? Okay, the point O correspond to the position of the central bright maximum and the points with path difference A sine theta equals to lambda 2 lambda are the secondary minimum. I just said whenever A sine theta your path difference equals to n lambda, you will have your minimas, secondary minimas. Clear? The secondary maxima are the point in between secondary minima. Yes, between two secondary minima. Check here. Where are the secondary minima? Lambda and 2 lambda. Yes, lambda and 2 lambda are secondary minima. And between them, there is your secondary maxima at 3 lambda by 2. Yes or no? Okay. So the secondary minima is the point in between the secondary minima or of decreasing intensity. If intensity of I at I naught, then the intensity at first secondary minima is found practically is about I naught by 9. Means if your intensity here is I naught, here the intensity becomes I naught by 9. मतलब reduced by 9 times. Okay. Yes, in their interference, Young's double slit experiment, intensity was same every time. And at second secondary maximum, it is I naught by 25. Now here, it is first time it is I naught by 9, and for second time it is I naught by 25, and so on. Width of secondary maxima. Width of central maximum. What is the width of central maximum? So the width of central maximum is the distance between first secondary minimum of either side of the point 2. Yes, this is your interference here. You got your interference, and you will have, if you this is secondary minimum, then this is the width of your secondary maximum, sorry, primary maximum or central maximum. This is your width. Okay, means if this distance equal to x, this also has to be equal to x, and x plus x equals to 2x. Clear? So x plus x equals to 2x. You need to find this 2x. What is exactly 2x? Okay. So the width of central maximum is the distance between the first secondary minimum on either side. Means there is secondary minimum first side, secondary minimum second side. So width, this total width is called width of the central maximum. If P is the position of the first secondary minimum and OP is equal to X, I said this OP is equal to X, then A sine theta, yes, this is point O, this is point P. We consider this distance is equals to X. We will make it 2X later on. So A sine theta, for first minimum, A sine theta is equals to n lambda, because just I derived A sine theta equals to n lambda. So for first minima, A sine theta is equals to lambda. So sine theta is equals to lambda by A. Clear or not? Now for a small angle, sine theta is approachable to theta. So sine theta is equals to lambda by A. So this you can write sine theta is equals to theta. Theta is equals to lambda by A. And for a small angle, theta is near about equals to tan theta. So tan theta equals to lambda by A. Clear? Now from the diagram, tan theta. What is tan theta? Tan theta is equals to perpendicular upon base. Okay. So this is your perpendicular, that is x, and base is the distance here, and this is your angle theta. So what is tan theta is equals to perpendicular upon base. So tan theta is equals to becomes x upon d. So x upon d equals to lambda by a. Now the value of x equals to d lambda by a. Clear or not clear? D lambda by a. But the central maximum width is twice. So you have the central maximum width equals to 2d lambda by a. Clear or not clear? This is your central maximum width of central maximum during diffraction. Now talking about angular width. What is your angular width? Okay. So if this upper angle is theta, then this also angle equals to theta. So you need to find the angular width. So find the angle. Angle is equals to arc upon radius. Angle equals to arc upon radius. See here. This is angular width. This is your angular width. Yes, this is your angular width. Like you got, this is your linear width twice. Okay. And angular width means how much angle it is making at the center. So this is your angular width. Okay. So by the diagram, this is your 2x and this is your angular width. Okay. It may be equals to 2 theta. Clear? Now angle is equals to arc upon radius. Now this radius is equivalent to d. So angle 2 theta is equals to arc. Arc is equals to 2x, and we just have calculated what is 2x. 2x is equals to 2x equals to d lambda, 2d lambda upon a. Yes or no? 2x equals to 2d lambda upon a. So place their value. 2x equals to 2d lambda upon a. Angle equals to arc. So this becomes 2x equals to 2d lambda upon a. This becomes arc divided by radius. Now radius here is here d. So d to d cancel. Your answer 2 lambda upon a. So angular width equals to 2 lambda upon a. Okay. Yes. So angular width is equals to theta is equals to 2 theta is equals to arc upon radius. Arc becomes 2x. Radius becomes d. D and d cancel out and final answer equals to 2 lambda upon a. Then note. Note point is there, student. When source is emitting a white light, then the diffraction pattern is colored. Yes, of course. Uh, when a source is emitting a white light, there are too many wavelength. Okay, and so the diffraction pattern will be colored. The central maximum is white because all the color will interfere there, but other band are colored as band width is proportional to lambda. So the red band is higher wavelength is wider than the violet wavelength and the smaller wavelength. Actually, we got the uh, angular width and linear width. We just find the linear width x equals to linear width 2x equals to 2 lambda capital D upon the slit width. It may be small a or small d. So you see the width of the slit. Okay, you can say width W is proportional to lambda. Proportional to lambda. So as red color wavelength is higher than the violet color wavelength. Clear or not clear? So width for the red color will be greater than the width for the violet color. Means if you're taking a white light that is consist of 7 different colors, so that time you getting the red color band is wider than the violet color band. Clear? Yeah. So therefore, red band is higher wavelength is wider than the violet band with a smaller wavelength. Now diffraction between difference between interference and diffraction. This is very important question in examination. Interference and diffraction. So what happened? It is due to the superposition of the two distinct waves coming from the two different sources. So there we have seen the two sources S1 and S2, and we have performed the interference of the waves from the two different sources. Clear? And those sources are coherent. Here, it is produced as the result of superposition of the secondary wavelet coming from the different part of the same wavefront. Yes. So this is because of a single wavefront. A single wavefront, there are so many wavelets, and from a single wavefront, there are so many wavelets when they interfere. So these are called secondary wavelets. So this is because of the superposition of secondary wavelets coming from the different part of a same wavefront. Okay? Yes. So there are two wavefronts, but here in diffraction there is only single wavefront. In interference pattern, the bright fringes are of same intensity. Yes. Earlier I told you that the interference during in the intensity of the brighter band and darker band are same everywhere. In diffraction pattern, all the brighter bands are not of the same intensity. You know, the central one having the highest intensity is I naught. Then after the first secondary maxima having an intensity of I0 by 9. Then after the third secondary maxima having an intensity of I naught upon 25. So it is gradually decreases. Clear? In diffraction pattern, all the bright bands are not of the same intensity, rather they are continuously decreasing. Okay. Talking about fringe width during an YDSE Young's double slit experiment, we see that this was lambda d upon a small d. The width of the interference fringes may or may not be equal. The width of the interference fringes may or may not be equal. Yes. Uh, If you have taken monochromatic light, then the fringes may be equal. This is also true. But the fringes width of diffraction bands are unequal. They may be equal. Sometime they are equal, but here the fringes width are not equal. Yes, here in this diagram you see the width are not equal. The central width is maximum, then after it is not equal. Okay. So fringes are of not equal, but here in interference, the fringe width is given by beta is equals to lambda d upon a small d. Okay, so you take it equal. No, not requirement right to write may or may not be. These are supposed to be equal. Numerical. Question number. Next question, students. How does the angular separation between the fringes of a single slit diffraction experiment changes when the distance of the separation between the slit and screen is doubled? Means when you have made D, you have made D in the place of D, you have changed D with capital 2D, you just double the distance between the source and screen, then how your angular separation, angular width varies. So what is the formula for angular width? Angular width is given by theta is equals to lambda by A. Clear or not clear? So 2 theta is equals to 2 lambda by A, no problem. So total angular width is equals to 2 theta is equals to 2 lambda by A. So you see, is there any term of capital D? No, it is independent from the distance between source and screen. Here the theta is independent from the separation between slit and screen. Clear or not clear? This is independent from the slit and screen. So angular separation remains the same. Okay, there will be no change in the angular separation. Clear? Done. Okay, students, see this question. The intensity of the instant intensity at central maximum in a Young's double slit experiment is I is naught. Okay, so here it is given. Central maximum intensity is given I naught. So we know for central maximum angle equals to 0. Clear? So for central maximum, phase angle equals to 0 degree and path difference equals to 0. If the distance CP equals to 1/3 of fringe width, yes, CP, the distance CP. So what is CP? First, this need to be understood. If the distance CP equals to 1/3 of the fringe width of the pattern, show that the intensity at a point P becomes I naught by 4. Okay, so given that the distance CP equals to 1/3 of the fringe width. So what is CP, students? CP means the path difference. I think it may be clear by the diagram. Where is CP? Yes, here. This is CP. Sorry, it is not path difference. It is the position of your fringe. Okay. So CP is given by X. So X is here equals to 1/3 of the fringe width. So 1/3 of the beta by 3. Okay. So come to the yes question. So it would be X equals to beta by 3. So beta is equals to the formula for beta fringe width is d lambda by d. So X into d lambda by d. Solve this one. So X small d upon capital D is equals to lambda by 3. Clear, students? This is becomes xd by a small d, a capital D. X small d upon capital D equals to lambda by 3. Now calculate the path difference. Path difference equal to BP minus AP. Path difference equals to BP minus AP. Now here this is what this is X. Okay, path difference BP minus AP equals to dx upon d. It is given equals to lambda by 3. So students, actually here the value of delta path difference is taken xd upon d. How? Let us see in this diagram. So if these waves are interfere at an angle theta, then you check please. This would be the path difference between the two interfering waves, because this is the length A to P and this is B to M. Okay. And if you draw the perpendicular, then this length is called path difference. So in this triangle, theta is there. So theta is equals to, for a small angle, theta is about 10 theta. So theta is equals to perpendicular upon base. So perpendicular becomes here BM, that is equals to delta. upon base, this is equals to d. Perpendicular upon base, so delta is equals to d into theta. So the path difference delta equals to d multiplied by theta. Clear? Now theta, again theta is equals to tan theta. Now come to the this one triangle. Mm, yes, this one triangle that making an angle theta here. Check this one triangle. In the terms of this position x, okay? So tan theta is equals to perpendicular here is equal to x and base here equal to d. So place the value path difference d into in the place of theta that is equals to tan theta. The value of tan theta is equals to x upon d. So this is equals to capital small d x upon d. So that's why we get the value here of dx by d. Okay, path difference equals to how much? Dx by d. Okay, so x equal to 1 upon 3, x equal to beta by 3, that is equals to 1 upon 3. The value of beta is equals to d lambda by d. We got this value of x. Now path difference bp minus ap, by the diagram it is equals to dx by d, and we got the value of dx by d is equals to lambda by 3. Okay, so finally we have the path difference equals to lambda by 3. Clear? Now, using this path difference, we have to find the phase difference. So, yesterday we read that the formula between path difference and phase difference, that phase difference equals to 2 pi upon lambda into path difference. The formula for phase difference equals to 2 pi upon lambda into path difference. So, multiply 2 pi upon lambda into lambda by 3. You have got an angle of 2 pi by 3. Okay. Now come to the relation of intensity. Yesterday we have derived the relation of intensity for the two interfering wave. I is equals to I naught cos square phi. Yes or no? Intensity for two interfering wave, intensity resultant intensity. See the relation. We already have proven this. I is equals to I naught cos square phi. Where is the formula for intensity? Yes, yes, this is the formula. Like I is equals to I naught square cos square phi I equals to, check here, this is equals to 4a square. So this is becomes 2a square hmm, cos square phi. So I equals to I naught square and cos square phi by 2 cos square phi by 2. So this is the formula for the resultant intensity I equal to I naught square cos square phi by 2. Clear? Hmm. So put these values here in this intensity relation. Yes. Check here. You can also derive this formula by using this. You can also get this formula. I equals to I1 plus I2 plus 2 I1 I2 cos phi. If the both the wave having intensity I naught, like two waves are interfering here. Okay, two waves are interfering at a point, both having intensity I naught. Then this formula becomes resultant intensity IR equals to I naught plus I naught. First having intensity I naught, second having intensity I naught plus 2 under root of I naught under root of I naught. So 2 under root cancel each other. I naught and I naught will result a single I naught and cos phi. Clear? So I resultant intensity equals to, this is become 2 I naught plus 2 I naught cos phi. 2 I naught plus 2 I naught cos phi. Now make 2 I naught as a common. So I resultant equals to 2 I naught I have taken as a common. So here it is equals to 1 plus cos phi. Now formula for 1 plus cos theta. 1 plus cos theta in mathematics. 1 plus cos theta equals to 2 cos square theta by 2. So here it will be 2 I naught. Okay. Yes. So here it will be equals to 2 I naught. 2 I naught multiply the value of 1 plus cos phi equals to 2 cos square phi by 2. So 2 into 2 becomes 4 I naught cos square phi by 2. So this is the formula for resultant intensity. Okay, you can make here. So IR is equals to 4 I naught cos square phi by 2. So we have applied here the formula for resultant intensity. I is equals to I naught cos square phi. If the intensity of the central fringe is I naught, then the intensity at point P where the phase difference is phi is given by I naught cos square phi. Wait, some problem is there. I have derived the formula that is different that I have got here. I equals to I naught cos square phi. Hmm. But this is not the formula for the resultant intensity. If the intensity of the central fringe is I naught, then intensity at point P. Okay, okay, okay. This has been related with the central fringe. Wait. Okay, students. So we get the phase difference equals to 2 pi by 3. Now make the formula for intensity for any phase angle. I is equals to I naught cos square phi. Okay. This is what? This is intensity at the center point, at the central. So this is equals to cos square phi. Now put the value I is equals to I naught cos square 2 pi by 3. Clear? So cos 2 pi by 3, 2 pi by 3 means how much degree? It is equals to 120 degree. Clear? So place here the value of cos 120 degree equals to minus 1 by 2. So this becomes I naught into minus 1 by 2. A square is there, so place here is a whole square. So this is equals to I naught by 4. Done?